Welcome to This Explainer. Today, we are tackling a topic that literally trips up so many students on the Cambridge mathematics exams, but I promise you, it is completely conquerable once you learn the right moves. We're talking about surds. I actually like to think of solving exam questions on surds a lot like a gymnast executing a flawless routine. It requires perfect form, a totally solid foundation, and precise execution on every single landing. If you rush it, or if you don't know the core mechanics, well, you're going to lose your balance. But if you master the steps we're about to go through, your math is going to look elegant, effortless, and most importantly, it's going to score top marks. Oh, and before we jump in, make sure you subscribe to our YouTube channel, Ace the Exams, at acetheexams_igcse to excel in your Cambridge examinations.
So, here is our roadmap for today's routine. We'll start with the foundation, what surds actually are. Then our warm-up, the art of simplifying. After that, we'll get into the main routine of manipulating expressions. Finally, we'll cover the dismount with simple denominators and how to stick a perfect landing with complex denominators.
All right, let's step onto the mat with Section 1, the foundation. What exactly are surds?
Okay, let's look at the actual definition here. The textbook tells us that a surd is an irrational number. You'll frequently see it written out in the form a plus b root c. In this setup, a and b are just your standard everyday rational numbers, but c, the number tucked under the root, is an integer that is not a perfect square. Think of numbers like the square root of 2, or maybe an expression like 5 plus the square root of 3. Crucially though, not every square root you run into is actually a surd.
To see what I mean, compare the square root of 36 to the square root of 2. 36 is a perfect square, right? So its root is 6. A totally normal, rational number. But if you punch the square root of 2 into your calculator, you get this messy decimal that just goes on forever without ever repeating. That makes it an irrational number, and that is a true surd. Being able to spot the difference between the two immediately is absolutely critical if you want to avoid making silly, early mistakes in your exam.
Moving right along to Section 2, the warm-up, the art of simplifying.
This is where we build our strength. The most crucial point is summarized perfectly by this quote straight from the text. Look for as large a factor of the number as possible which has an exact square root. Seriously, I want you to memorize this. It's your golden rule. Whenever you're staring down a big, intimidating number under a root, your brain should automatically start scanning for its largest perfect square factor. Doing this right out of the gate is a huge pro tip for saving time.
To actually execute that golden rule, we need our primary tool. It's this core mathematical law. The square root of a times b is equal to the square root of a multiplied by the square root of b. It's a beautifully simple rule, but it is the literal foundation of simplifying surds. It gives us permission to take a big, clunky number, factor it out, and just break it apart into more manageable, bite-sized pieces.
Let's actually see this in action with an example from the source material. Say we need to simplify the square root of 72. Now, 9 is a factor of 72, and 9 is a perfect square. 4 is also a factor, and it's a perfect square too. But remember that golden rule we just talked about? We want the largest exact square root factor. If you spot straight away that 36 is a factor of 72, you save yourself so much hassle. You just rewrite the expression as the square root of 36 times 2. Then, apply our core rule to split them up into root 36 times root 2. Since the square root of 36 is just 6, we instantly arrive at our beautifully simplified surd, 6 root 2. See? It's a much more graceful and efficient solution than endlessly chipping away at the number with smaller factors.
Now for the heavy lifting. Section 3, the routine, manipulating expressions.
Before we start combining things, here are your rules of engagement. First, when you're adding and subtracting, you absolutely must deal with the rational parts and the irrational parts separately. You can't just mash them together. Second, all your standard algebraic expansions, they still apply here. If you have to square a bracket, you are still using your standard a squared plus 2ab plus b squared format. And third, when you add or subtract, treat the surd kind of like you would an x in algebra. You just group the similar terms together. Simple as that. By the way, if you're finding this helpful, stop scrolling and subscribe to our YouTube channel, Ace the Exams, at acetheexams_igcse to excel in your Cambridge examinations.
Let's look at an example that beautifully integrates algebra and surds. Let's square the expression 3 minus root 2. You expand this exactly like an algebraic binomial. It becomes 3 minus root 2 multiplied by 3 minus root 2. When we expand that out, we get 9 minus 3 root 2
minus another 3 root 2, and then finally, and honestly, this is the cool part, plus root 2 times root 2. Well, think about it. Root 2 times root 2 is just the whole number 2, so our expression cleans up to 9 plus 2 minus 6 root 2, leaving us with a final elegant answer of 11 minus 6 root 2. Notice how relying on those basic algebraic rules kept our structure perfectly balanced.
Moving on to Section 4, the dismount, simple denominators.
So, we often hear the term rationalizing, but what does that actually mean? Rationalizing a denominator is simply the process of manipulating an irrational fraction so that the bottom number, the denominator, becomes a nice, clean, rational number. And the absolute key here is that we have to do it without changing the overall mathematical value of the fraction. Having a rational number on the bottom just makes the fraction infinitely easier to work with in complex equations.
Let's look at a simple dismount. Take the fraction 5 over the square root of 2. To get rid of that pesky root 2 on the bottom, we just multiply both the numerator and the denominator by the exact same thing, the square root of 2. Because any number divided by itself is just 1, we aren't changing the value of the fraction at all. On top, 5 times root 2 gives us 5 root 2. On the bottom, root 2 times root 2 gives us the whole number 2. Our final fraction is 5 root 2 over 2. Just like that, we've elegantly cleared the irrational denominator and our fraction is perfectly balanced.
Finally, the hardest part of the routine. Section 5. Perfect landing. Complex denominators.
To tackle complex denominators, we really need our secret weapon. The source text gives us a massive hint in a margin note. Remember that x plus y times x minus y equals x squared minus y squared. This classic algebraic identity is called the difference of squares, and it is literally the exact tool we need to eliminate complex surds on the bottom of a fraction.
Let's see it play out. Take the fraction 6 over root 7 minus 2. That denominator is a bit messy. To rationalize this, we multiply the top and bottom by what's called the conjugate. The conjugate is the exact same terms as the denominator, but with the opposite sign in the middle. So we multiply top and bottom by root 7 plus 2. Why? Because of that difference of squares rule. On the bottom, root 7 minus 2 times root 7 plus 2 simply becomes root 7 squared minus 2 squared. That's 7 minus 4, which is 3. The complex, irrational mess completely disappears, leaving us with a nice clean 3 on the bottom. Then we just divide the top by 3, leaving us with a final simplified answer of 2 times root 7 plus 2.
So here is your 4-step complex rationalization strategy. Think of me as your coach here. Step 1, identify the denominator form. Is it a plus b root c? Step 2, multiply the numerator and the denominator by its exact opposite sign, a minus b root c. Step 3, expand the bottom using that difference of squares rule. And finally, step 4, simplify your arithmetic to reveal your beautiful, purely rational denominator. Memorize this sequence and I promise you will never stumble on these questions again.
To bring it all together, here is your ultimate cheat sheet, pulled directly from the key points of our source material. This shows you exactly which tool to grab based on your starting conditions. If your denominator is a simple root, like root b, just multiply the top and bottom by root b. But if you are facing a complex denominator like a plus b root c, you deploy the conjugate, a minus b root c. This allows the difference of squares to do all the heavy lifting for you. And there you have it. We've defined our terms, warmed up with simplification, executed our algebraic routine, and stuck the landing on both simple and complex denominators. You now know the complete mathematical gymnastics routine for Surds. But knowing the routine is only half the battle, right? The real question is, do you have the foundational strength to practice these steps until you can land every algebraic manipulation flawlessly on your next Cambridge exam? Go back to your past papers, drill these exact rules, and make sure your execution is flawless. Thanks so much for joining me on this explainer. And hey, here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Keep practicing, and I'll see you next time.